everyone. So I hope everyone's doing okay. I know this is a weird kind of period with this transition to remote teaching and everything that's going on in the world. So also, it's been quite a bit since we've kind of seen each other due to my conference being canceled with that hiatus plus the additional spring break. So what I wanted to do first is just before we move on to lecture 9 and the DFT, I wanted to kind of give a quick recap on kind of what I think the key aspects are in lecture 8. Which dealt more with the continuous Fourier analysis, and then basically just introducing the concept of kind of Fourier analysis. So again, we are dealing with basically looking at time, and specifically we're going to be looking at kind of inverse time space, which is frequency space. Same concept is used for XRD. So for X rate of fraction, you get a plot of like intensity versus 2 theta. And we use our good old friend Bragg's law, 2D HKL sine theta, to relate essentially distance and theta. Theta is basically inverse distance space or reciprocal space. Reciprocal time space, inverse time space. It's just 1 over meter space. But anyways, we had our fun, luckily we got to have our fun Fourier applications in person lecture. So we saw basically the lasers and all kind of that other cool stuff, and also kind of how we figured out the structure of DNA. But anyways, so we are going to be dealing with time. There are lots of different kind of ways that time can vary, so different signals. The beauty of Fourier analysis, specifically continuous Fourier transforms, CFTs, and DFT, is we could work and represent any type of these signals here. So we could deal with all of these types of signals using Fourier analysis. So, we basically break that down into basically functions, a sum of harmonics. So we kind of define what a simple harmonic is here. Again, this is kind of just a little bit of review from last time to define what a simple harmonic is. So second derivative equal, basically directly proportional, opposite in sign. That's a harmonic function. The really important stuff comes in this next basically page. So cyclic frequency versus circular frequency. So remember we had this definition, omega equals 2 pi f, where f is our cyclic frequency. That's going to be in units of hertz. Inverse seconds, so hertz over seconds. We have omega as our circular frequency here. That is going to be in units of rads per second. So radians per second. So when I ask for frequency in this course, or when we talk about frequency, we're always going to be dealing with circular frequency. However, when you look in your kind of sine of 15t, this is omega. So again, just to kind of be aware and cognizant of what's going on here. So circular frequency, cyclic frequency, here's the relationship. So we want to make sure that we have that definition. It's one of our first kind of key definitions we have to have in the back of our pocket so we can move forward. We showed some complex signals, and we can represent, again, any of these signals that vary in time with our Fourier series. So this, and I shouldn't, excuse me, I just erased, or let me erase this. This is our Fourier series. So we can represent any signal with this function here. Now, what do we have to do? I mean, this is a complex signal, but again, don't be too worried about it. We have to just calculate these harmonics. So AN, BN, these are our harmonic coefficients. And they're given basically an order. There are harmonic orders that depends on N. N is essentially the number of harmonics. So you see, in general, we can go to an infinite number of harmonics. Now, we obviously can't do that mathematically in real life. Instead, we're going to use the number of harmonics required to approximate our signal. So we will see that, basically, if you have a function, so this is my original signal, phi of t, let's say it looks like this. I'm going to switch colors. My Fourier signal will fit like this, and the fit will improve depending on the number of harmonics. Typically, as n increases, the quality of the fit, or your approximation, increases as well. So you'll see that, and we actually did that in class and also in the problem sets as well. But again, these are the number of harmonic coefficients, and that's what we're going to deal with there. And you can see that your frequency here is multiplied by the number of harmonic coefficients. We'll get back to that in a second. So one of the questions in the problem set gives you basically a function of y of t that has the harmonic coefficients. So you can tell, basically using this equation here, what is the largest, essentially, or dominant frequency? What's the maximum frequency? Again, we talked about that in class. We'll refer to that in just a second. But when I give you a harmonic, or when you're given a Fourier series, you can calculate what is your, lowest frequency, what is your highest frequency, and all that. That's given to you already in the signal. So there's no real work to be done on that part. So quick hint for the problem set question. So let's go a little bit down here. Again, went through a bunch of waveforms. You could, again, change your signal. We could change the amplitude, add phase lags. You could do lots of kind of cool stuff, special waveforms, sines, or square waves, triangle waves, sawtooth waves. All important things, but again, we're going to get a little bit deeper into kind of the analysis here. So unfortunately, I already wrote a little bit, so let me erase this really quickly. Now, we talked about that we want to look and analyze time signals in terms of, excuse me for erasing here. We wanted to analyze time signals in inverse time space, so in frequency space. So the way that we're going to do that is by plotting a frequency spectrum. So we have our harmonic coefficients a sub n and b sub n. We are going to plot the magnitude c sub n, which is just going to be a sub n squared plus b sub n squared, square root of that. So we're going to plot and generate a plot of Cn, the magnitude, versus frequency, where this obviously you have a null frequency of 0, but your first frequency here, f, is going to be your lowest frequency. So this is often referred to as f fundamental or delta f. And we're going to plot integer values, number of harmonic coefficients. So this is our first harmonic, then it's going to be 2f, then 3f, on and on and on until you reach your number of harmonics or infinite number of harmonics. So we are going to look at what is the magnitude of this. So this frequency spectrum is important because it tells you what's your lowest frequency, what's your highest frequency, just on the x-axis, and what is your dominant frequency. The dominant frequency, if you hear the word dominant, that refers to the magnitude of this, the Cn. So here, our dominant frequency is this highest, whatever has the highest amplitude here. So it happens to be that our maximum frequency and dominant frequency are actually the same. So more into this a little bit later. So you might be asking yourself, how do we calculate ANs and BNs? Well, just like we talked about in class, we can use this expression, but we don't want to work with this. We want to work with cyclic frequency. And we have this really handy relationship that typically we're going to be analyzing signals for a finite time period t. So your period is just going to be t. So that is going to be t. So when does the signal repeat? Does it repeat? Doesn't matter. Every signal will repeat over a certain period. Even if it's aperiodic, you could just analyze it for the time that you took that measurement. So we want to rewrite this in terms of, instead of omega, we want to substitute, get rid of those omegas. We want to work with cyclic frequency, or circular frequency, excuse me. Or sorry, cyclic frequency, excuse me. So we want to work with f, we don't want to work with omega. So we're going to substitute back in here, and then we're going to get to the expression that you all wrote down and know by heart now, which is this, in order to calculate our harmonic coefficients. So we'll look at an example, but y of t is basically your original signal. N is your harmonic coefficients. T is going to be your period. That's it. Integrate, solve, you're good to go. Calculate for how many harmonic coefficients you're asked for, and that's it. So when you're analyzing Fourier signals, these are kind of 4 common scenarios, but really we want to break it down. Case 1 is where we're going to perform this analysis up here. And this type of analysis is called the continuous Fourier transform. We can only perform a continuous Fourier transform when we know the mathematical function, when we know the algebraic form. So if I know my signal is y equals 10x, I could use CFT. For these other cases, we're going to have to use DFT. DFT is going to allow us to use a discrete Fourier transform. So basically, if we get a plot of points like this, so y versus time, we don't know, yeah, this curve may look like this, but who knows, in between this point, it could spike up, here. We don't know what the functional form is. So we are going to discretely analyze the points and then look at our frequency space. So more on this in lecture 9. Let's look at and remind ourselves how to do CFT. So lecture 9, so coming up soon. So let's look at our first example. So let's look at the frequency spectrum. We want to determine the frequency spectrum from this is our original signal. Now I want the frequency spectrum and I want to calculate the Fourier series as well. So first thing we want to ask ourselves is, if we want the frequency spectrum, we need to calculate this. Like I already mentioned, we already know how to write this. Pi of t times cosine 2 pi n t over period dt. Let's just double check to make sure I'm right. And what do you know? We got that. So what is our period for this expression? Where does the signal repeat? So it goes up, flat lines, down, up, flat lines, down. So 2 seconds is my period. But it's also periodic over 3. Like I could go up, down, up, then, or I could do a 4. It could be 6. You'll see you always want to pick the shortest period, because that's going to make your life easier in terms of plugging into this equation in a second. So pick shortest period to make your life a little bit better. All right, so you plug that in there. What is our y of t? This is a little bit more complicated expression, right? So you want to break it up piecewise, right? We don't know this, this kind of expression just as one equation, but let's break it up into, from 0 to 1. Let me kind of erase here. From 0 to 1 seconds, what is my y of t? Well, my y of t from 0 to 1 is just going to be 100t, right? What about from 1 to 2? Well, my y of t is just going to be 100. So with this information known, I can now start to plug and play into this equation here. So I'm going to actually erase, or actually add some space. Actually, this is just perfect. So if I want to calculate a sub n, I am going to substitute it in. So now it's 1. I'm going to break it up from, 2 over 2 times from 0 to 1. It is going to be 100t times cosine of 2 pi nt over 2 dt plus from 1 to 2, 100 times cosine. It gets very relaxing. Again, I would suggest, we've seen in class how to solve this using Mathematica. I would use this a lot in this course. So, do you remember the chain rule? Because I definitely don't, but I could plug this in Mathematica and I could figure out and solve my harmonic coefficients that way. So let's go to the next page here. You can see the expression. You could go double check your answer. I have also attached basically my Mathematica notebook, so you can kind of double check and play around with that set of code, and we might see that in an additional lecture, or actually we'll probably do that in another YouTube video as well, just to kind of double check. But that's it. You'll have your CNs and your amplitudes, and you can kind of solve after that. There's another example here written in the notes that we've gone over again in class that shows, again, a little bit more slowly and thoroughly. But again, it's the same procedure, right? So in this, I have from 0 to pi. So this is pi. This is 2 pi. So from 0 to pi, my y of t is 10. From pi to 2 pi, my y of t is 20. What is my period? Well, the shortest period is going to be 2 pi. I also know a relationship between, if I want to find my lowest frequency, excuse me for skipping over this, my lowest frequency, so my F fundamental, my F lowest, also called delta F, is just going to be 1 over t. So my lowest frequency that I plot, and we're going to see that actually in the frequency spectrum here in a second, is going to be 1 over t, so 1 over 2 pi. So you'll calculate your harmonic coefficients. This kind of goes through the math. And again, you could read this a little bit slower. If you're interested in reading this, again, I have not the OER, but I will provide a link to the lecture notes. If you are reading this not in my class or having hard time accessing it via Stellar or Canvas, excuse me. So once you calculate those values, you can plot your frequency spectrum here. So notice, again, it's the amplitude, but this first peak here that's not 0, that is going to be your delta F. And each of these after that, so this is 1 delta F. This is going to be 2 delta F. This is 3 delta F. And on and on and on and on and on to how many ever delta Fs you have. So we always plot basically, again, because it's your harmonic coefficients. N harmonic coefficients times delta F. So this is your first, second, third, etc., fourth, fifth, sixth, etc., blah, 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 blah. So here we got to identify, this is our F max, this is our delta F, your fundamental, and this also has to be your dominant frequency. Yep. So that's it. And you can see here, our red is our original signal. This is our Fourier series. So you can just plug in, once you have your harmonic coefficients, you could plug in and plot your Fourier series. That's the blue here. And it's pretty good approximation. As you increase your harmonic coefficients, this is going to get tighter and tighter and tighter. So it'll approximate your curve better and better and better and better. And at infinity, there'll be essentially no difference. So that's the beauty of basically Fourier analysis. So there's another example in here. So there's tons of examples, or not tons, but there's lots of examples that you can kind of look and play around with. And again, any of these graphs, if we know this value here, I know the period, because this delta F is just going to be 1 over the period. There's lots of information you can gain by just looking. This is your critical kind of engineering toolbox, right? Because a dominant frequency can be like a resonant frequency. So if you're building a bridge, and you know there's some vibration that's occurring, like as the cars go across that bridge, you better make sure that it's the same as the resonant frequency. Otherwise, that bridge is going to start to kind of wave and fluctuate and alternate like crazy. So this is a key toolbox for us to kind of analyze signals in whatever system you're working with. And again, Fourier analysis expands beyond engineering, beyond biology. It's a really kind of critical tool that any engineer, any scientist needs to have in order to kind of analyze and be kind of really productive, scientist or engineer. So, yeah, that's pretty much. Again, we've kind of covered this pretty well during lecture, but again, it's been a while since we've seen each other. So, yeah, I hope this helps. If there's any other questions, you want more examples, if there's any issues with the problem set, please let me know. I'll be happy to provide some more worked examples. And yeah, so please stay healthy and stay safe. And yeah, have a great day. And next time we'll talk about DFT, so converting those integrals to summations. Have a great day.